Hello everyone and welcome to the first lecture of Applied Cryptography. There are several topics that we will cover in this lecture. We will talk about random and pseudo-random numbers, we will discuss one-time pad and stream cipher encryption schemes, but then we will also look at the basics of computer science, bits and bytes, different ways how we can represent binary data, and we will also study bitwise operations, which we will use heavily, at least in the first two programming tasks of this course. But let's start with the first topic, which is randomness. Randomness is a super important topic in cryptography. Now, each of you has heard this word and have some intuition about its meaning. But how would we describe or define it? So what is a random sequence? Let me give you a few possible definitions. For instance, a random sequence is a sequence of numbers that does not follow any deterministic pattern. So in a random sequence, there should be no patterns. If there is a pattern, then we can predict what follows, right? A similar definition, none of the numbers can be predicted based on the previous numbers, and vice versa, the previous numbers should not be predictable based on the current numbers. Another definition has no description shorter than itself. And this is a pretty neat definition because, indeed, if there are no patterns, we cannot describe it shorter than itself. Or, in other words, sequence of bits that cannot be compressed. Because compression essentially means describing something large using a shorter representation. For example, if we have 1 GB file full of 0 bytes, we can compress it by providing a shorter description. For instance, we can replace it with a short text that states that here should follow 1 GB of zeros, without the need to store all these 0 bytes, right? Right. So one way to check if the data is not random is try compressing the data. If it compresses well, most likely it is not random. This is also the reason why you would want to compress data before applying encryption. Once you have encrypted the data, the result should look totally random and it should not be compressible. Now, where do we need randomness in real life? Not in the computer world, but in the real world. Can you give some examples? When was the last time in your everyday life where you said to yourself, it would be very nice to have some random numbers right now? As an example, perhaps you have seen randomness being used in sports to decide which team should start the game, or perhaps in a lottery to randomly choose the winner. But let me give you a more peculiar example of a simple daily business transaction where we actually are forced to engage in a cryptographic protocol and use some randomness to not get deceived. Let's suppose that we want to buy strawberries from an open market. So here is a seller who sells strawberries and in this small box here provides some free sample berries for us to taste. Of course, the question is, how can we be sure that the sample berry here is representing the whole content of the basket? To avoid getting tricked, we should try a berry that we ourselves have picked out from the basket, right? But then, if customers always pick berries from, let's say, this corner here, and the seller could predict it, the seller could cheat again, distributing the sweetest berries to this corner, right? So you see, this is a nice example which illustrates that randomness can be quite useful to guarantee fairness not only in the computer world, but also in the real world in such basic transaction as this one. The next question is, why do we need randomness in cryptography? Well, I hope it is obvious that we need to generate secrets such as keys, passwords, and nonces randomly, because otherwise, if an attacker could predict these, the entire security of the system may get compromised. Now, where can we get random numbers in real life? Can we flip a coin to get a random number? Yes, we are using this method in practice, for example in sports, but does the coin flipping really produce a random result? Actually, we could argue that there is nothing random, because the result of the flip depends on the laws of physics, the amount of force we apply, the direction of wind, and so on. So perhaps you can even train a skill to influence the result. So this is not a perfect method to generate random numbers. Can a computer program generate random numbers? Or in other words, can we write an algorithm which generates random numbers? No, we cannot, because there is no randomness in the computer. The computer is designed to precisely execute the instructions given to it. In fact, the processor must not introduce any randomness or errors, unless maybe it is overclocked and overheats. Yes, you can write an algorithm which does something based on the random input, but the algorithm itself cannot be the source of the randomness. So there has to be some physical source of randomness. It turns out that in nature, there are just a few sources that can be used to obtain true randomness. And these are thermal noise, photoelectric effect, and quantum phenomena. Not important to remember, just good to know. So if we want to generate true randomness, we will have to use one of these natural sources. Okay? All right. In cryptography, very frequently we use a function called Pseudo-Random Number Generator, or PRNG. The prefix pseudo here indicates that it is not a true random number generator, but something less perfect. So what is it? It is a deterministic algorithm that produces endless stream of numbers, which is indistinguishable from truly random stream of numbers. The output of PRNG is completely determined by the seed value passed to the function. It means that if we run PRNG twice with the same seed value, we will get exactly the same pseudo-random output. What happens internally is that this function takes the seed value and mixes it with itself forever, generating an output that looks like random output, cannot be compressed, has no parents, the next and previous values cannot be predicted, and so on. Of course, this indistinguishability holds only if the attacker does not know the seed value. If the seed value is known, the whole output of PRNG can be easily regenerated. So, while strictly speaking, the numbers generated by PRNG are not truly random, since in practice it is very hard to distinguish them from truly random, assuming that the seed is unknown. They can be good enough for practical needs. So, each computer operating system usually has a PRNG built into it, and whenever a program asks the operating system to provide to it some random bytes, the PRNG built into the operating system will provide them. The question we may have is, what value does the operating system use to seed its PRNG? Because to guarantee security, the seed value used by the PRNG must be unpredictable by the attacker, right? As an example, let's look at the Linux dev-urandom implementation of PRNG. So this dev-urandom is a device file from which we can read to get some random bytes provided by the operating system. Here is a simplified illustration of how the PRNG implementation works in a Linux operating system. So the idea is to collect all kinds of system events: mouse movements, audio noise, keyboard presses, performance counters, and others, to mix them all together and use it as a seed value for the PRNG. The PRNG will then stretch the seed into the endless stream of pseudo-random bytes, time to time updating the internal state, adding in some new events. Now, we could argue that, for example, these key presses here are not that unpredictable in real life. For example, the attacker could observe the timing of our key presses, right? However, the point is that in practice, it is very hard, if impossible, for the attacker to reconstruct all these inputs used to construct the seed value. So, while theoretically not perfect, in practice, it is believed to provide good enough security. The latest Intel and AMD processors provide a RD-rand instruction that can be used to get truly random numbers from the processor. If available, a Linux kernel will use it as an additional source to construct the seed. There were expressed some concerns whether we could trust that processor manufacturers had not backdoored the RD-rand instruction. But the good news is that as long as we don't rely exclusively on RD-rand to construct the seed value, we are safe. So a very important property of the PRNG is that knowing some part of the input does not allow anything about the output to be predicted. For example, if we know the mouse movements here, we should not be able to predict the first X bytes from the PRNG output. It should be all or nothing. We can predict output only if we can guess all the bits of the seed value. Okay? Usually, PRNG is used when a true random number generator is not available or the use of true random number generator to generate large amounts of randomness is expensive. In such a case, we can use true random number generator only to generate the seed value and then use the fast and cheap PRNG to generate as much pseudo-random numbers as we need. So you can think of PRNG as an algorithm which extends randomness. However, a very important point is that the entropy, or the amount of uncertainty of the output, depends on the entropy of the input. If we see the PRNG with a 5-byte seed value, the entropy of the output will also be 5 bytes, regardless of the fact that the PRNG will generate gigabytes of data. So the security or entropy of the generated data will still depend on the entropy of the input value. Okay? All right. Now, is it possible to tell whether some given sequence is random? Here is an example. Is this sequence random? Do you see some pattern? Can you predict the next digits? I cannot see any pattern, but it turns out that this is not a random sequence, as it is the math constant pi, where it is possible to generate all the remaining endless stream of digits. So this is not a random sequence because it has a shorter description than itself. That is, to describe this value, we can simply say math constant pi or provide a pi generation algorithm. On the other hand, what about this sequence? Well, I see some pattern. Do you? Turns out that the fact that there is some visible pattern does not immediately mean that this sequence could not have been produced by a true random number generator. In fact, there would be something very wrong if this sequence would never be produced by a true random number generator. As a rule, if we generate enough random data, it is guaranteed that we will find our full name there. The question is only about the probability. If we generate gigabytes of data and it is all zeros, then, well, something most likely is wrong. In fact, there are statistical randomness tests which can be used to test randomness. These two are the most popular sets of randomness tests. What is important to note, however, is that these tests are not able to prove that the sequence is random. They are only able to prove non-randomness. The tests look for patterns, and if these patterns are detected in a large enough sequence, then it may indicate that the data does not come from a true random number generator. All right, before we move forward, we have to take a look at the basics of computer science, bits and bytes. So what are they? A bit string is a string of bits, zeros and ones, as shown here. We can convert the bit string to a decimal number using the following method. We look at the positions where the bit is 1, take 2 into the power of position, and add the result together. For example, we take 2 to the 0 plus 2 to the 1 plus 2 to the 7 plus 2 to the 11, and we add these together, and the result is the value in the decimal system. Then we have the term most significant bit, and this bit is the leftmost bit. So this bit here is the most significant bit. Why? Because if we change this bit, the value changes more significantly than we would have changed any other bit in the bit string. Similarly, as in the decimal system, the most significant digit of the number is the leftmost digit. Then we have bytes, which are collections of 8 bits. So one byte can have 256 different values, from 0 to 255. Why do you think one byte is exactly 8 bits? Why not, let's say, 6, 7, or 9? The answer is that we have historically agreed that one byte is 8 bits. What is important about the byte is that it used to be a basic addressable element. For instance, if we wanted to read some data from memory, we would specify which byte to fetch. And then, if we were interested in only a few bits, we would then take the bits we need and throw away the rest of the bits. Okay. And then there is the ASCII Table, which is a standard that assigns each byte value a specific printable or non-printable character. ASCII is a standard method to encode textual data. For instance, if we wanted to send text ABC over the wire, we would send 3 bytes. The first with value 97, the second with value 98, and the third with value 99, ABC. As you can see, using this table, we can encode only the Latin alphabet and a few additional diacritic characters. To encode more exotic alphabets, we need to use the Unicode standard encoding, which uses 2 or more bytes to encode a single character. Then we have a hexadecimal or base 16 encoding, where one hex symbol or character represents 4 bits. Therefore, 2 hex symbols are needed to represent a byte. For example, the hex symbol 2 here encodes 4 bits of the value 2. And the hex symbol E here encodes 4 bits of the value 14. So we need 2 hex symbols to encode 1 byte. We will be using hex encoding to print out binary data, because this encoding is easy to work with. The drawback, of course, is that hex representation needs double the space, because we need 2 hex byte values to represent a single byte. A more space-efficient encoding is base 64 encoding. Here you can see how base 64 encoded data looks. The idea behind base 64 is that we represent binary data using printable characters. These are alphanumeric characters and characters plus, /, and the equals character. And since base 64 encoded data uses more printable characters than the hex encoding, then base 64 encoded data is only 33% larger than the binary data that is represented using base 64. Here is how base 64 encoded data is produced. What it does is that it encodes 3 byte input into 4 ASCII characters of output. Not important, no, but maybe helpful. So base 64 encoding is used for data storage and transmission, where the data must contain only printable characters and where we need something more space efficient than hex encoding. Visually interpreting base 64 encoding data is harder than hex because byte boundaries of original data does not match the byte boundaries of the base 64 characters, as you see here. Therefore, base 64 is not good for data interpretation. Let's now spend some time studying the bitwise operations, AND, OR, XOR, and bit shifting. They will be important for the homework and for the topics that we will discuss further in this course. Every one of you should know these basics, but it turns out that in reality students are not used to apply these bitwise operations in practice. These basic bitwise operations are very powerful, because using these as building blocks, we can implement all other arithmetic and logical operations, for example, division, multiplication, and so on. Let's take a look at how these bitwise operations work one by one. Let's start with bitwise AND. The idea here is simple. Let's say we want to perform bitwise AND on these 2 bit strings. The result of this operation will be another bit string where ones are only in the positions where in both bit strings the bit was 1. So in this case, only this bit will be 1 because here both are 1s. Okay? Okay. Why this operation might be useful is because we can use it to extract bits we are interested in. Let's say that this is our original bit string. If we want to extract these 2 bit values, then we can perform bitwise operation with another bit string, we call it a bit mask, where these 2 bits are set. So the result will be a bit string where all bits are zeros, with the bit values in these 2 positions being copied into the result. So these 2 bits go here in the result. In Python, we can use this ampersand character to perform bitwise operations on 2 integers. The next operation is bitwise OR. Here the idea is that the result will be 1s in the positions where 1 was at least in one of the bit strings. So this is 0 because both are zeros. This is 1 because at least one of the bits is 1. This is 1 also because at least one of the bits is 1, and so on. This operation is useful to set specific bits. Let's say we have here the original bit string and we want to set these two bits to ones. To do so, we apply bitwise OR with this bit string where these two bits are set. As a result, we get the original bit string, but in these two positions, the bits being set to ones. In Python, we can use this pipe character to perform bitwise operation on two integers. Now, the favorite bitwise operation of a cryptographer is XOR or exclusive OR. Here the idea is that in the result we have ones only in the positions where exactly one of the bits was 1. If both are 0 or both are 1, then the result is 0. So you see, here this is 1 because here exactly one of the bits was 1. Here it is 0 because both bits were 0. And here it is 0 because bits here both were 1. This operation is useful to flip specific bits. Let's say here we have some bit string and we want to flip or invert bits in these two positions. To do that, we XOR this original bit string with this bit string where these two bits are set. As a result, we will get the original bit string, but in these two positions, the value being inverted or flipped. You will see why it is useful in a moment. In Python, we can use this hat character to perform bitwise operations on two integers. The last bitwise operation is bit shifting. Here the idea is that we can shift bits right or left and pad with zeros. We can see here an example of this bit string being right shifted by two positions. As a result, these two 0 bits being pushed out. And if we want to do the opposite, we can left shift this bit string by two positions. This will move every bit to the left, and here pad with zeros. The bit shifting is a very efficient method to multiply or divide a number by 2. Every right shift will divide the value by 2, and every left shift will multiply the value by 2. In general, division and multiplication are quite complex arithmetic operations, but the division and multiplication by 2 can be performed very fast using this bit shifting operation. In Python, we can use these two bigger than characters to right shift, specifying on the right how many bit positions to shift. And for left shifting, we have to use two smaller than characters. I hope that it is clear. Very good. We are done with the bitwise operations. Now, let me introduce the first crypto system of this course, one-time pad or OTP. This crypto system is very special because it provides 100% secure, unbreakable encryption. And I am not kidding. You probably have heard that nothing is 100% secure, and with enough effort, every crypto system can be cracked. Well, this is not the case here. Yes, most of the crypto systems can be cracked using enough computing resources, but not this one. Unfortunately, we won't see these type of crypto systems in practice, and you will see why very soon. The second reason why this crypto system is special is because it is super simple. I can assure you that you will be able to understand how it works and be able to implement it using, let's say, pen and paper. But anyhow, whenever we discuss some crypto system, there are three things that we have to define. First is how do we generate the key, second is how do we encrypt something, and third is how do we decrypt. The key generation here is very simple. The key, or the so-called one-time pad, is a random string the same length as the plaintext. So if we want to encrypt a 1 GB file, we have to generate a 1 GB random key. The encryption operation is XORing the plaintext with the key, and the decryption operation is XORing the ciphertext with the key. Here is how it looks. So we have Alice and Bob, who share the same key, or one-time pad. Alice encrypts the plaintext by XORing it with the key, The ciphertext is sent over the non-confidential channel to Bob. Bob takes the ciphertext, XORs it with the one-time pad, and recovers the original plaintext. Now, there are two things that we have to discuss. First is why it works. Why XORing the plaintext and then XORing it again, we get back the original plaintext. And the second, why it is secure. Why someone who obtains the ciphertext cannot crack it no matter how much computing resources they have. The first question, why it works. Why XORing the plaintext twice with the same data, we get back the original plaintext. Now, if you remember, we can look at the bitwise XOR operation as the flipping of specific bits. So when we XOR plaintext with the key here, we flip bits in specific positions of the plaintext. If we XOR it once more, we essentially flip the bits in the same positions back to their original values. Hence why on the decryption we get back the original plaintext. The second question, why is it secure? So what happens when we XOR plaintext with random data? If this is random data, it means that on average half of the bits are zeros and half of the bits are ones. But we as an attacker have no idea which of the bits are zeros and which are ones. Since it is random data, each bit has the same 50% probability of being 0 or 1. So this XORing will flip half of the bits in the original plaintext, but the attacker has no clue which of the bits were flipped. Basically, by XORing any data with some random data, we destroy all information in the original data, and the result is effectively some other random data. Now, can the attacker crack the ciphertext by generating all the possible keys here and trying to XOR the ciphertext with these keys until he finds the plaintext? Yes, if he has a lot of computing resources, he can try each and every possible key. But the problem is that there is no way for the attacker to detect when he has found the correct key. Since the key and the plaintext is of the same length, there exists a unique key for every unique plaintext. If the attacker applies one key, he will get the decryption feed the kitty. If he applies another key, he will get the plaintext kill the president. Since both of these plaintexts have the same probability of being the original plaintext, there is no information that can help the attacker find out which was the original key and hence the original plaintext. Anyone actually can find a key that will transform the ciphertext to anything they like, but they cannot prove that it was the original plaintext. And that is why brute forcing one-time pad is of useless. But then there are a few preconditions for one-time pad to be information theoretically secure or unbreakable. First, the key one-time pad has to be truly random. There must be no biases. Every value has to have the same probability of appearing. And second, and related one, the key must never be reused. If we used the key to encrypt one file, we cannot reuse it later to encrypt another file. And here is why. Let's assume that we use the same key to encrypt two plaintexts. So here we encrypt plaintext 1 and obtain ciphertext 1, and here plaintext 2 and obtain ciphertext 2. Now, what happens if for some reason the attacker knows or guesses the content of plaintext 2? What he can do is he can XOR ciphertext 2 with plaintext 2, and what will he obtain? He'll obtain the key, because the key is the difference between the ciphertext and plaintext. Once he has the key, he can XOR it with ciphertext 1 and get plaintext 1. Not nice at all. So here, by knowing one plaintext, the attacker was able to decrypt another plaintext, which is a very bad flaw of a crypto system. Therefore, the key must be random and never reused to encrypt different plaintexts. One-time pad is neat because it can be applied using pen and paper, as you can see here. So you would have a paper sheet with keys, and you would strike out the key once it has been used. The problem with one-time pad is that you will not see it being used in practice. The reason is because to encrypt a 1 GB file, you have to generate and securely exchange a 1 GB key. we could actually argue that if you have a secure channel to exchange this 1 GB key, then why not to use it to exchange the plaintext directly, right? So with cryptography, we usually do not solve problems completely, but convert one problem to another, easier one. For example, instead of ensuring the confidentiality of this 1 GB file, we only need to ensure confidentiality of some relatively short key. In this context, one-time pad does not seem to help us reduce the size of the problem, right? There may, however, be scenarios where the use of one-time pad makes sense. For example, it may be useful in cases where you have access to a secure channel now, but you want to exchange confidential information later, when the secure channel is not available anymore. For example, in a spy scenario where the spy has to travel to a distant location and then send encrypted messages over insecure channels. So, one-time pad is not that useless, and in some specific scenarios may actually be the best crypto system to be used. But alright, that is how the one-time pad crypto system works. Now, once we understand how the one-time pad works, we can immediately understand how stream ciphers work, because the stream cipher works exactly as one-time pad, with the difference only in the key generation procedure. So in stream cipher, a small key seeds the pseudo-random number generator, and the output of the PRNG is used as a key stream for encryption and decryption. Here is how it looks. We specify a short key as a seed, and the PRNG will generate a key stream as long as the plaintext. On the decryption, the same key is used here, and therefore the PRNG generates the same key stream as here for encryption. So the stream ciphers differ only by the PRNG used here to generate the key stream. Otherwise, the construction of stream ciphers follow the same principle. Now, while the one-time pad crypto system is not used in practice, the stream ciphers are widely used everywhere. For instance, voice encryption in your mobile phone uses stream cipher, and most likely all other real-time voice applications also use stream ciphers. The use of stream cipher becomes very practical because the key, or the seed here, does not have to be the same length as the plaintext, meaning that it can be very short. The drawback, however, is that stream cipher is not 100% secure and unbreakable. So the question is why it is less secure than one-time pad. Why now an attacker, by trying out all different potential seeds, is able to find the correct seed that was used for encryption? The reason is because there does not exist a unique key for each unique plaintext. Assuming that the encrypted plaintext is much longer than the key, there will likely exist only a single short key that will produce a decryption that is meaningful. All the other incorrect keys will produce plaintexts that will look pretty much random. Fortunately, if this key is long and random enough, in reality nobody will be able to try out all possible combinations to find the correct key, and therefore it is safe enough to use this crypto system in practice. A very important point which you have to realize is that encryption on its own does not provide integrity. Confidentiality and integrity are two different things. Let's consider the following example. Let's say we encrypt some plaintext and send the ciphertext here over an untrusted channel where the attacker can modify the ciphertext. So what will happen on the decryption if the attacker flips a single bit here at the middle of this ciphertext? The result will be that after the decryption, the result will be the original plaintext, but with the bit flipped in the same position where it was flipped in the ciphertext. Now, is this a big deal in practice? Is it exploitable? If the attacker knows the structure of the plaintext, he indeed can influence the plaintext in a meaningful way. For example, let's assume that this ciphertext contains a bank transaction encoding the amount of money and the bank account where the money should be transferred. If the attacker knows the place in the ciphertext where the amount is encoded, by flipping the bits in the respective positions, he can change the value. If he knows the account number where the money is to be transferred, by flipping the needed bits, he can replace it with his own account number, and so on. So as you see, this is a pretty serious issue. Therefore, usually encryption is not enough, and we need some extra mechanisms to ensure also the integrity of the ciphertext. We will look at these mechanisms in the next lectures of this course. Now, another important point here, the same as for one-time pad, is that the same key stream must never be reused to encrypt different plaintexts. Otherwise, this will result in the same weakness as if you reuse the same one-time pad. This essentially means that we cannot reuse the same key here to encrypt different plaintext files. So how can we solve this issue? One solution is that we can agree with the recipient on several keys, which we then rotate after each encryption such that the same key never repeats. But actually we can do better. We can reuse the same key, but after encrypting each plaintext, we can modify it in some predictable way. And here is the idea. The solution is, on every encryption, add a unique nonce to the key. Nonce here means a number that is used once. So both parties here share the same secret key, but the sender, in every encryption, appends to it a unique nonce. This nonce does not have to be secret. The sender can send it together with the ciphertext. The recipient will take the nonce, append it to the key, and hence the PRNG will produce the same key stream as was used here in the encryption process, and thus we'll be able to recover the original plaintext. Now, why is it safe to send this nonce as a plaintext to the recipient? What happens if an attacker learns this nonce? Does knowing the nonce help the attacker crack the ciphertext? No, it does not, because the attacker knows only a part of the seed value. Due to the properties of PRNG, as long as the attacker does not know the entire seed value fed to the PRNG, the attacker will not be able to reproduce any part of the key stream that was used for encryption. Very good. Now the requirement is that the same nonce must never be reused. If we reuse the same nonce, the key stream will be the same and we are screwed again. So how to generate the nonce such that it never repeats? And this is where we enter in the world of engineering. Here you can see a very common problem between the theoretical cryptography and practice. A cryptographer will come up with a crypto system, mathematically prove its security, and then just say that yes, it is secure, assuming that the same nonce is never used. The cryptographer usually will not care much how hard or easy it is to ensure that this requirement is fulfilled in practice. Anyhow, so what are the potential methods to generate a nonce that never repeats? One idea is that we could generate it randomly. If the random value is sufficiently large, then the probability that it would repeat is negligible, right? Very good. Now the question is where to get these random numbers. It may actually be quite expensive to build a random number generator into our system, and if the random number generator malfunctions and produces the same value, we are in trouble. Perhaps a better idea is to use a counter value as a nonce. The requirement for a nonce is just that it has to be unique. We can start with 1, 2, 3, 4 and continue incrementing it for every plaintext we encrypt. Here the problem is that our system has to store this value somewhere. If it forgets it or fails to update, the same counter value will be reused and we are in trouble again. Yet another idea is to use the current date and time as a nonce. Since we know that the time always keeps increasing, this should work, right? This, however, assumes that our system has access to a trusted time source that cannot be manipulated by the attacker, which again is quite a strong assumption to make. So as you see, each of these methods has its drawbacks. Probably the best we can do here is to combine or concatenate all these three values together, and this way our system will be secure as long as at least one of these values have not been reused. So at first it may seem that this is an easy problem to solve, but in practice it is not that trivial. And this is the reason why stream ciphers should be avoided if possible, for example, using block ciphers, which we will discuss in the further lectures. Alright, so here are some questions about the topics we discussed in this lecture, and you should now be able to answer them. Very similar questions will be asked in the exam. Therefore, try to write down answers to these questions immediately after watching the lecture. This should give you a good understanding of the topic and will also help you to prepare for the exam. But okay, That is it for the theory. Let's move to the practice. The homework task for this week is to implement the one-time pad crypto system. It should work in two modes, encryption and decryption mode. Encryption should produce a random key file and encrypted output file. Here we assign the executable bit to our Python script, and then we run the script with the following command-line arguments. The first argument is the mode encrypt. The second argument is the file name of the file that we want to encrypt, so the file name data file should exist at this point. This is the file name where the randomly generated one-time pad should be written, and this is the file name where the ciphertext should be written. The decryption should use the key file and produce the encrypted original plaintext file. So we run our script with the decrypt mode. This is the file where ciphertext is stored. This is the file where the key is stored. And this is where, after the decryption, the plaintext will be written. Once the solution is ready, commit the otp.py file to your Bitbucket repository. Add the file, commit the changes, and push the changes to the remote Bitbucket repository. Okay? The solution has to be committed using this precise file name and must be located under directory 01, where 01 denotes the first homework. For the second homework, it must be 02 and so on. Check the grading page. It will show whether the homework solution was found in your repository. This is the homework template available in the course repository. There are two helper functions that you have to implement, and the functions encrypt and decrypt. The arguments to these functions are the file names received from the command line. Here is a short introduction into Python 3 string and bytes data types. So in Python 3, string objects store Unicode characters. Here is how we can define a string variable containing some text characters. The type function will return class str, and the length function will return number of characters in the string object, which is 3 in this case. In Python, we can access every character separately by using the Python slice operator in the square bracket specifying the index of the character starting from 0. Now, what is important to realize is that to write such a string into a file or send it over the network, we first need to encode it to bytes, because at the end of the day, the data has to be expressed in bytes. There are several encoding methods to encode these Unicode characters to bytes. The most popular one is UTF-8 encoding scheme. We can encode string object to bytes using the encode method on a string object, and we will get back a bytes object. Bytes object stores bytes, and this bytes object we can then write into a file, for example. Now, if we try to print out text representation of that bytes object, we will see something like this. This B prefix indicates that this is text representation of bytes object. Character F is printed as it is, but non-printable byte values are printed in hex representation. The type method now returns bytes, and the length method returns 5, because these 3 Unicode characters using UTF-8 encoding method were encoded to 5 bytes. 1, 2, 3, 4, 5. Then we can run the decode method to decode bytes back to a string object, as you see here. Now, if we need to define the bytes object, there are two options. If the bytes only consist of the printable ASCII values, then we can use printable characters as shown here. Otherwise, we have to use the byte method specifying a list of integer byte values. So both these methods produce the same bytes object, as you can see here, A, B, and C. Now, if we want to access a specific byte value in the bytes object using index, we will get back the integer value of that byte. If we want to get a bytes object containing that single byte, we have to specify a range in the slicing operation like this here. Finally, if we want to convert bytes to base 64 or hexadecimal representation, we have to use Python's codex module. Codex encode, here is the bytes object, and the encoding scheme base 64 in this case. Or in this case, hex encoding. The encode method will return another bytes object, but it now contains bytes values containing ASCII values of the base 64 or hex representation. For printing the value out, it can be converted to string object using the decode method, and this is a string object now. In case of hexadecimal encoding, there is a shorter way to do this, because bytes object have a hex method that can be called and which will perform encoding to hex and will return string object. So we can use this as a shortcut if we need to print out some binary data in textual hex representation. For decoding the data back from base 64 or hex representation, we can use the decode method from codex module. All right, let's talk about bytes conversion to integer. In some cases, we may have a need to represent some arbitrary data as one big integer. This is needed because some cryptographic algorithms such as RSA, which we will study later in this course, work using integer arithmetic. So the first thing we have to do is to convert the data we need to encrypt to an integer value. This we will also need to do in this homework. So how can we do it in Python? Let's say we have this bytes object which contains 3 bytes, A, B, and C, and we want to convert it to one big integer. First, we can get the integer value of the first byte here using index 0 here. What we get is the byte value of character A, which has value 97. And if we use bin function, we can look at the bit string representation of the integer value. Now, what we can do next is that we can left shift this I by 8 positions. We will shift this bit string to the left by 8 positions, and we will have 8 extra zeros here. And the point now is that the value of this B here, we now want to set here in these 8 bits. What we do is we take the integer value of B and we bitwise OR it with I. So we are setting these bits here. And this is the result. This is our A, this is our B, and what we're missing is the value of C here. Again, we prepare the space for the C byte by left shifting. And again, we load the byte value of C here using the bitwise operations. Finally, this is our integer representation of these 3 bytes A, B, and capital C. I hope you see the idea. Convert the first byte to integer, left shift integer 8 times, convert the second byte to integer, load second integer in the first 8 bytes, and so on. In the homework, you have to implement this algorithm which converts bytes to integer and vice versa, takes an integer and converts it back to bytes. You have to figure out how to reverse this algorithm using bitwise operations. How you would extract these rightmost 8 bits here, append it to the bytes object, then right shift this value, extract the next 8 bits, and so on. The goal of this lecture and homework is for you to understand these bitwise operations, to get an idea of how you can use them to convert bytes to integers and integers back to bytes. Do not skip the understanding of this idea, because the next homework will be all about mangling with bits and bytes using bitwise operations. Take your time to figure out how the bitwise operations work, because this first homework is just a warm-up compared to the second homework. Okay? Okay. So, step by step, what should be the algorithm of your solution? For the encryptor, read the plaintext file content into bytes object. For example, this will open this file in read-only binary mode, and the read method will return bytes object with the content of the file. Then, convert plaintext bytes to one big integer using the algorithm shown in the previous slide. Next, obtain random key the same length as plaintext. Use Pseudo-Random, specifying here the number of random bytes the operating system should return. Next, convert key bytes to one big integer, and then XOR plaintext and key integers. Please use this approach. Don't try to use any other approach for XORing. Okay? Then save the key and XORed result ciphertext to file. And for that you have to convert ciphertext integer to bytes object. To stress it once more, please use bitwise operations to achieve this. If you use any other approach, your solution will not get full points. For the decryptor, perform all the operations in reverse order. Okay? Alright. The test case. As a test case, we create ciphertext and key file with specific values and try to decrypt ciphertext with the key, and we should get back the plaintext with this value. Here we are writing these 4 bytes in a file, and then we run hexadecimal to verify that these 4 bytes have indeed been written into the file. The second test case is that we create a plaintext file, try to encrypt and decrypt it, and as a result, we should get back the same original plaintext. It is important to note that when we are converting byte string to integer, we are losing the most significant bits, 0 bits. For example, a gigabyte of zeros and 1 0 byte will both encode to integer 0. Therefore, for converting integer back to bytes, we have to specify to how many bytes the integer should be encoded. This is the reason why this test case here starts with 0 bytes. So make sure that in the decryption process, these 0 bytes are not lost. Okay? Now, a tricky question to you. What do you think? Is this one-time pad implementation secure? Well, the problem is that the key here is not generated using a true random number generator. Therefore, your one-time pad implementation will not provide 100% security. Theoretically, an attacker can brute force the internal state of the pseudo-random number generator of your operating system, and therefore this implementation will not achieve information theoretical security. And a similar warning applies also for all the other crypto systems that we will implement in this course. We are implementing them to understand how they work, but this is by no means a security audited code that should be used in real-world systems. You will also see why later in this course. Finally, some general requirements for this and all the future homework tasks. The first thing is that please include information of how much time the task took for you to implement it. This can be included as a comment at the top of your source code. Simply specify in hours how much time you spent. This does not affect your grade in any way. This statistic is important to understand the relative complexity of homework tasks so that the points can be better distributed for the tasks the next time the course is given. So please be honest in your time reporting. Give feedback about parts that were hard to grasp or implement, or you have some idea for improvement of the slides and so on. This you can write in the homework solution as a comment, or you can simply send me an email. Do not waste your time on input validation. If the function accepts some value, you can assume that a correct value is given. You don't have to add checks that verify the correctness of submitted data. It is completely fine if your solution crashes on wrong input. When you write production software, sure, you have to validate inputs. Here, you can skip that part to save time. Do not use imports libraries that are not explicitly allowed. All the dependencies that are needed to solve the homework will always be defined in the homework template. If you want to reuse some code from the previous homework solutions, you have to embed that code in your solution. Your solution must be one self-contained file. The output of your solution must byte by byte match the format of example output shown on the slides. Do not invent your own output format. Remove any non-required debugging output from your solution before pushing the solution in your repository. Unless explicitly required by the task, the solution must not create, delete, or overwrite any files on the file system. Commit the solution to the main branch of your repository with the file name required. Don't push unfinished versions in your repository. If you see that there is a solution in your repository, we'll assume that it is finished and we'll grade it. Sure, you can submit unfinished version which you don't plan to improve, and it will be graded proportional to the functionality implemented. But don't push into remote repository work versions unless you want them to get graded. Okay? And as a side note, it might be a good idea to start working on the homework as early as possible. This way, you may receive feedback before the deadline, and this will give you an opportunity to fix your solution before the deadline, thus obtaining the maximum score. Also, try not to skip the first 2 homework assignments. as they will serve as a basis on which many of the following homework tasks will be constructed upon. Alright, okay, that is it for the instructions. Thank you for your attention and good luck with the homework.